Alright, welcome back to another section of Chapter 7. In this half of the chapter, we're going to be looking at exponential and logarithmic equations, and we're going to be solving them and working with that. The first part of the chapter is just figuring out what these things are. And so, without further ado, after I get my laser pointer going, we're going to look at exponential and logarithmic equations and inequalities. And most of what we're going to be doing is going to be focused on equations. We'll take a little look at inequalities at the end. Our learning targets today: I can solve exponential and logarithmic equations and inequalities. That is profound, I'm sure. The second one, I can solve problems involving exponential and logarithmic equations. It's word problems. They set up pretty much right for you, so that's not too big. We'll be getting into more types of word problems in the next section, but for now, they're going to be basically pretty easy. So, ways of solving exponential equations. We have two main methods that we're going to use. The first one is trying to write them with the same base. Now, by them, what do I mean? I mean the bases. We have 2 to the x, we have 4 to the x plus 1. 4 is 2 to a power, so we could write this as 2 to a power. Specifically, 4 is 2 squared. Now here, we have a power times a power. No, we have a power of a power. Sorry. A power of a power. What do we do when we have a power of a power? We multiply them. So we'll have 2 to the 2x plus 1 times 2 to the x. Now, if we have 2 to a power equals 2 to a power, wouldn't it make sense that these exponents have to be equal to each other? Well, sure enough, they are. So this just becomes x equals 2 times x plus 1. That's just a linear equation. We've been solving these for years. We can distribute the 2, can subtract the 2x, and then negative x equals 2, so x equals negative 2. So this all started out again by writing this 4 as 2 to a power so that they're the same. Well, in this case, we only had to change one side. It's possible that we could change both sides. Now, it's also possible we could write 1/4 as 1/2 to a power, but that's nowhere near as easy. I would get it to a whole number to a power. It's just easier to think about. 1/4, that's 4 is 2 squared. To get it in the denominator, it's 2 to the negative 2. 1/2 is 2 to the negative 1. We can then multiply the exponents on each side. So we have 2 to the negative 4x equals 2 to the negative x. 2 to a power equals 2 to a power. Therefore, the powers, the exponents, have to be equal. Negative 4x equals negative x. Now, at this point, sometimes people start freaking out because they're like, well, but negative 4x equals negative x, they can't be equal. They can. Just solve it like you would. Move the x's to the same side. I'm going to add 4x to both sides. 0 equals 3x. Divide by 3, x equals 0. Can x equal 0? Sure, x can equal 0. If we plug 0 in up here, we have 1/4 to 0. Well, 1/4 anything to the 0 equals 1. This anything to the 0 also equals 1. 1 does in fact equal 1. It works. And people think, well, but can't we plug in 0 all the time? No. 2 to the 0 equals 1. 0 plus 1 is 1. 4 to the 1 equals 4. 0 does not work here. Otherwise, we would have gotten it for an answer down here. So just trust your answer. It's okay. For another method, we'll have things like this. 4 to the x equals 10. So if we tried this using the first method, writing them with the same base, well, 4 is 2 to a power. 10, however, is not 2 to a power. Well, 10 is 2 to the power. 10 is 2 to the 3 point something. But that is not something we want to try to figure out. So we have a second method for this type of problem. And in the long run, this is going to be the more common type. And that is, we're going to take the log of both sides. You can do basically anything you want to an equation as long as you do the same thing to both sides. That includes taking the log of both sides. And we're just going to take the log base 10. Why would we take the log base 10? Because you can do it in your calculator. So if we take the log of both sides, we're going to have log of 4 to the x equals log of 10. Now, if you remember back to our properties, there was one that I said was going to be very important when we started solving equations, and that would be the power property. What can we do with this exponent? If your answer was, we can move it out to the front and multiply it out there, you are correct. And so we can do that. We have x times log 4 equals log 10. Log 4 is just a number. Log 10 is just a number. In fact, log 10 equals 1, but it doesn't have to be a nice number. These are both numbers. We have a number times x equals a number. How do we get x by itself if we have a number times x? We're going to divide by that. Well, the number is log 4, so divide by log 4. And then at this point, it becomes a calculator issue. We're going to type log 10 divided by log 4. Specifically, I would not do that as one step. I would do that as a couple steps. I would go log 10, enter, then divide by, it'll pull up the answer. In this case, it's just 1, doesn't matter, but it'll pull up the answer with all the decimals. So you have log 10, enter, divide by log 4, enter. And you're going to get something, it's like x equals 1.6609, blah, blah, blah. Round it to 3 decimal places, and you'll be fine. But we don't want to round till the very end. In this case, the answer is the end. In the next problem, the end, like that part won't quite be the end, but it'll be close. So again, we took the log of both sides, which meant we could bring the exponent out in front, divide by the log, and we get x equals an irrational number. And if you really want to try that, go forward to the answer that you'd have in your calculator, and you'll come out to be something really close to 10. There's a little bit of rounding error, so you'll get like 9.9999 blah blah blah, or 10.00001, but it's as close as we can get. So let's look at the next one. The next one, we have 2.4 to the 3x plus 1 equals 9. I chose this one because, oh my gosh, 2.4 is a decimal. Nobody cares. Just deal with it. We're going to take the log of both sides, because 9 is 3 to a power. It's not going to be 2.4 to a power, at least not a pleasant one. So, log of both sides. And this allows us to bring the exponent out in front. That would be the whole exponent, 3x plus 1. So we have 3x plus 1 times log of 2.4 equals log 9. Log of 2.4 is going to be a very unpleasant number. Log 9 is going to be a very unpleasant number. There's a couple ways you could do this here. You could take this log of 2.4 and distribute it, which just kind of spreads out the unpleasantness. I'd recommend dividing it first. So you get this 3x plus 1. That's nice. Equals log 9 divided by log 2.4. What happens when you take an unpleasant number and you divide it by another unpleasant number? The answer is you get only one unpleasant number. It's possible to come out to be a nice number, but at the very least, it's going to take the ugliness from these two irrational numbers and make it just one place. And so it's going to be about 2.5, blah, 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 blah. Nobody cares what that number is. You can write something down, like I just have 2.5. I know that's a really, really bad estimation for it. But that's not the answer. I'm going to keep that number in my calculator. And again, to get that, I want log 9, enter, then divide by log 2.4, enter. I think it's like 2.503 or so. And I'm just going to solve for x. So I'm going to take that number that's in the calculator from what I did this, minus 1. And then enter, divide by 3, and x is about 0.503. That's the step where we're going to round and put our 3 decimal places down. Up here, this is just part of the work. It doesn't have to be perfectly accurate because you're using the number that's actually in your calculator. This is not something we'd want to do by hand. This is not mental math. This is the type of stuff that you would not have had on a no calculator test. You really need a calculator for this. So, our two methods, we can write them with the same base, and then the exponents are going to be equal, or we can take the log of both sides and then solve for a variable. So, why don't you try a couple? The first one, 2 to the x minus 1 equals 1 over 64. Hint, use method 1. 1 over 64 is 2 to a power. Second one, 1/2 to the negative x equals 1.6. I would use method 2 on this one because otherwise that's not going to be pleasant. So go ahead, pause this, and then come back to it when you're ready. Oh, sorry about that. All right, welcome back. How'd you do? So for the first one, 1 over 64, that's going to be 2 to the negative 6. And so that means x minus 1 equals negative 6. Add 1, x equals negative 5. It's a lot easier than you'd think it would be just by looking at this. Like, ooh, 4 steps. How about over here? Take the log of both sides. So we got log of 1/2 to the negative x equals log 1.6. The negative x can come out front. We can divide by log 1/2. And this is just a number. Do it in your calculator. Log 1.6. Enter. Divide by log 0.5. Enter. To get negative x equals negative 0.678. And then x multiplied by negative 1. X equals 0.678. So those would be exponential equations. This is one of the bigger pieces of the section. So if you can do this, you're well on your way. We also have logarithmic equations. Now, they don't come in quite as many, like you don't see as many views of these. They come in really one of two types of questions. The first one is where we have a log on both sides. Log base 2 of 7x plus 1 equals log base 2 of 2 minus x. Now, if you're looking at this thinking, log base 2 of something equals log base 2 of something, shouldn't these somethings be equal in order for this to be equal since they're the same base? And if that's your thought, you would again be correct. If log base b of x equals log base b of y, then x equals y. So that means that 7x plus 1 equals 2 minus x. And then it's just solving a linear equation. We can add x and subtract 1 to get 8x equals 1. Divide by 8, x equals 1/8. The only way that this could be made a little bit more challenging is if we had to combine a couple logs using our log properties. But even still, that's not going to happen so much right now, because in order to do that, we'd end up with x squareds. We're not quite ready for that yet. But that's really the only way. What if these two bases weren't equal? Well, that would be a whole nother headache, and that's, again, beyond the scope of what we're actually going to be doing. So that's one type of ways that we can see logarithmic equations and solve them. The other type is if we have log base something equals a number. Notice here there's only one log. Over here there are two logs. And so if there's only one log, what we do is we're going to make both of them exponents. And so when we make both of them exponents, we put them as exponents of this base. It's like going backwards from what we had over here solving logarithmic. If they had the same base, the exponents were equal. Well, if we can make these the same base of that, because 6 to log base 6 of 2x plus 3 is just 2x plus 3. There's another way of looking at what we did here. All we did is we wrote this as an exponent. Doesn't this line mean 6 to the 3 equals 2x plus 3? Right? Like that. 6 to the 3 is just a number. In fact, it's 216. We can subtract 3 and then divide by 2 to get x equals 106.5. And so that's our second way. We can take it to the power, but that's mathematically what we're doing. You can also just rewrite it as an exponent. 6 to the 3 equals this. In fact, you did that on a couple worksheets and a couple problems already without knowing that's what you're supposed to do. So, again, two methods. Go ahead and try a couple. We have log base 3 of 7x equals log base 3 of 2x plus 0.5. And log base 2 of 1 plus x over 2 equals 4. Go ahead and pause, see if you can get these, and then come back when you're ready. How'd we do this time? So, this one, well, 7x is going to have to equal 2x plus 0.5. Subtract the 2x to get 5x equals 0.5. Divide by 5, x equals 0.1. That one was probably pretty easy is my guess. How about over here? Rewrite it. 2 to the 4th equals 1 plus x over 2. 2 to the 4th is just 16. Subtract 1. So x over 2 equals 15. Multiply by 2. X equals 30. How'd you do on that one? Pretty easy. It's amazing that we didn't need a calculator for these, right? Well, it is possible. This might not equal 4. It might equal 4.7, in which case 2 to the 4.7 is, again, just a number. You can find it using your calculator. And so that's logarithmic equations. Again, there's not as much with this as there is with exponential equations, because most of the time we see things exponentially, and we use logarithms to help fix that. So now using tables and graphs, and this is where we're going to get to inequalities. If we have something like 2 to the x times 3 to the x is less than or equal to 7,776, how do we solve that? Use your graphing calculator. Graph it. If we graph it, we're going to get something that looks kind of like this. I know my calculator looks a little bit funny. It's a different kind of calculator. I'm on a different computer at the moment. But it's exponential, which we should expect. Well, it goes up pretty quick. Take a guess. What do you think that this x is going to be to get it to 7,776? Is it going to be big? Is it going to be little? Well, go to the table. See what the table has. Mine's a split screen. So when x equals 1, it equals 6. That looks about right. When x equals 2 is 36. Then 260. Wow. X equals 5 gets us to 7,776. How many of you guessed 5? Were you thinking it was a bigger number than that? Hopefully not much of a smaller number. But that's what it is. So that's where it's equal to. Well, what values make it less than? Well, when x is less than 5, it's less than. So x is just less than or equal to 5. And that's how you do tables and graphs. You're just using your calculators, type it in, look at your graph. What are you looking for? So that was section 7.5. Anyway, I'll see you in class for a quick activity, and I'll see you then.